Hello, this is the chapter 29 homework preview. I'm sorry this comes out a little bit delayed. I was too occupied with other things to make this earlier. My apologies. So the chapter 29 homework is on magnetism, and it looks, when you first open it up, it looks pretty long. There are over 30 questions there, but as always there's a fair amount of extra credit, so if you're just worried about your final grade, as it were, you don't quite have to finish actually all of them to get the full points. But also, a lot of them are actually really quite short and just sort of test an individual concept. So even though there's lots of them, you should be able to go through them very quickly. In this preview, I'm going to go through some of the problems, actually a fair number. You see them here before you. In the first video, the one you're watching right now, I'm going to go through those, 3, 8, 12, 20, and 21. Second one, I'm going to tackle the next row, 22, 26, 28, 33, and 46. And the last one, I'll tackle those three. As always, I'm not going to necessarily work all of them through to the end, right? I'm going to leave some bits, pieces for you to do, so you actually think about it. But that'll give you a fair amount of pointers to get started on that. Let's get started with number 3. This is the setup for number 3. Number 3, we have a proton, and we assume the proton is at the origin of some coordinate system. We're defining our coordinate system to have the proton at the origin right now, and it's moving along the x-axis. Again, right, physically speaking, we're just saying there is a proton that's moving in some direction, and then we're defining our coordinate system to match this setup. So we're asked to find the magnetic field at the points I marked in different colors. At 1, 0, 0, this is in centimeters, 0, 1, 0, it's in the y direction, and then 0 minus to 0, that's in the negative y direction. Notice in magnetism you almost always have to think in 3D, right? Because of this cross product that keeps showing up that requires 3 dimensions to make sense. So it is a moving particle, right? A charged particle creating a magnetic field, and that magnetic field is going to be given by the Biot-Savart law, the one I wrote down up there, in 2 different versions, right? Once explicitly with the cross product, and once where the cross product is spelled out as a magnitude and essentially the sign component. Of course, for this one, we'd have to then add that we need to use the right-hand rule to determine the direction. Okay, so there are different ways of doing this. You could work out the cross product directly. That'll work nicely. I'm not going to work out for you in this preview the actual numerical values, right, of this and this. You can plug in the proton charge here, the distances, right? They're always, so r is always the vector that points from where the charge is to the point where you want to find your magnetic field. So if I just withdraw this for this one here, this would be my r in that direction. I think this was part B. I'm going to put a little b here. First one is this one here. So let's do this. This is my first vector, RA. And then this one here is going to be the third part of the question, RC. Right, so the R that appears up here is that vector that connects the essentially the position of the point where you want to find a field relative to the charge. Now, of course, this kind of setup does produce a constant magnetic field, right? If I wait a moment, the particle will move down the axis. It's then over here, and so the field that was strongest around here before is now strongest here. So this is not a static setup where you get the same magnetic field in the spot, but we're just worried about right now when the proton is here, what is the magnetic field at the marked points. So how about we solve this by just some different method for each part, right? Just to sort of see different ways of actually evaluating this. So for part A, I'm actually not going to do very much at all. Let's look at part A. In part A, the point where I want to find the magnetic field is in front of the proton in terms of it's in the same direction as the proton. So what do I have here? I have that for part A, the one at the red point, right? I have that RA, the connecting vector between the proton and the point where I want to find the field, is parallel to the velocity of the proton, of the charge. What does that mean? It means the angle between them is 0. Now, if you remember your cross products, because you've watched the lecture videos on that, you remember that the cross product is 0 when the two vectors are parallel to each other. And we see this right here in this expression here. Because if they're parallel, it implies the angle between them. I'm going to call this RV, subscript, which means like the angle between R and V. The displacement and the velocity is 0. So the sine of the angle is 0. The sine of the angle is 0. Well, then that whole thing is 0. So for this one, I'm just going to get that B equals 0. Right, there's no real direction because it's 0. 0 doesn't have a direction. That was, in a way, the easy one. Alright, now let's do part B. And for part B, I'm going to very explicitly use this one here. So I'm going to work it out using this expression here. So I'm going to have B is equal to, I know it's down here on the page, just mu naught over 4 pi, so those are just constants, and I'm going to let you figure out what those are, times Q V sine theta between R and V divided by the distance squared, and then using the right hand rule. Alright, so I look at this, and because this is along the x-axis, this is along the y-axis, the angle between them, right here, between the direction of the velocity and the displacement is 90 degrees. So that means I've got theta, RV, is 90 degrees, so the sine of theta RV is just 1. So this is 1, and the rest is just plug in. When you plug in values. I've noticed in this expression here, similar up here too, the R on the bottom, right, that is just the length. I didn't put like a little arrow on top of it. So this is not a vector, this is just the magnitude. Sometimes, like writing R is kind of a shorthand for writing the magnitude of the vector. If I write V, I mean the magnitude of the vector, right? It's a very common shorthand notation because we're lazy and don't want to clutter up our equation with lots of extra symbols. So this is just a lot neater to write than this. Notice that in this expression here, by the way, this is R hat, right? Which means I'm not taking the vector R itself, but I'm just taking its direction and imagining it has a length 1. Which is why the R that's up here doesn't come in up here because we're multiplying it by 1. Right? That's why the R seems to have disappeared in the expression up here. Because it's R hat, which is a unit vector. Alright, but so you plug in the values. Make sure, of course, you convert to meters, because the distance are in centimeters. You convert to meters. You plug in, and you get the magnitude. So that gives you the magnitude of B. Okay, but what about the direction? So this is where we're going to use the right hand rule. So you take your right hand, not your left hand, and you point the first vector, right, that forms the cross product, point in the direction of the velocity. It's V cross R, right? So the first one is V. So V goes in the direction of velocity. I'm going to turn the page a bit, so I can actually do this way, right? Velocity this direction. R in this case is that direction. That's my index finger here. Then my middle finger, which way can I stick it out? Upwards. That means along the Z direction. So the field over here is across is upwards, right? So the answer is here. B is, you work out the numbers, pointing. I'm going to write upwards. Of course, more technically, that is the positive Z direction, right? Because it's pointing straight up, which is parallel to the Z-axis, and it's in the same direction, not down, not the opposite, but the positive, towards positive Z. Right? That'd be one way to figuring this one out. So then for the last one, for this one here, let me actually work it out with the cross product. So I'm just going to work out the cross product itself. Now again, I trust you can plug in all the values. So for C, you'll have that B is equal to mu naught over 4 pi, just numbers, you can plug those in. Proton charge, you can plug that in. V cross R hat divided by R squared. Now, all of those are just values you plug in, right? The R in the case of C is going to be 2 centimeters because the vector R is that. So R, let me write this out. And this should be familiar to you, but I realize some of you may not have done very much work with vectors. Minus, I wanted to convert it to meters. Right, so this is my R vector. Or we can write it in the IJK notation if you prefer that. That's my V vector, right, is the value was 1 times 10 to the 7. So I'm going to write this as 1 times 10 to the 7, 0, 0. Right? Because it's in the x direction, x, y, z, x, y, z. So, okay, so I'm not going to ignore all of those bits because they're just plugging in values. The question is, what does the cross product do? So I'm going to evaluate it by the sort of the crosswise method. Or you can use the one method with like you draw this like matrix determinant and you sort of do diagonal lines this way, diagonal lines this way. There are different ways of evaluating it. This one should be fairly easy with lots of zeros. So V cross R. What's that? So I'm going to write down again. 10 to the 7 is 1 times 10 to the 7, 0, 0. Cross product 0 minus 0.02, 0. Okay, let me color code this. So for the these two vectors make one vector, right? So for the x component here, the x component of the new vector, I'm going to take the y of the first one and multiply it with this one here, and I'm then going to subtract this minus this. Now this 0 times 0 is 0, 0 times 0 minus 0 times minus 0.0002. Of course, the whole thing is a 0. This is 0 times 0, 0 times something else, who cares? It's all 0. Okay, so that was that. It was easy. Now let's figure out the y component here. For this one, remember you sort of move one down. You can do the trick where you copy out the first and second row again down here if you're more comfortable doing that. Why not? Let's do it that way. So one trick you can do to evaluating, for doing the mechanics of evaluating cross product is write it down like this in the column form, and you just copy out the first 2 rows again, sort of underneath it. And then to get this one, so I go on my y component, so I start on the next one down, I go down minus this. So what do I have now? I've got 0 times 0. That's boring once more, right? Minus, when you go the other way, it's always minus. 1 times 10 to the 7 times 0, again, that's going to be 0. Now what's the last one? The last one is my z component. The z component, I while I do this. The alternative would have been that I connect this one right to the top one again, right? And sort of go round the loop. You find your own best way of solving those, whatever you like best. So in this case, I've got 1 times 10 to the 7 times minus 0.02. It's this way, and then minus 0 times 0. So the only thing that's not 0 is this times this, right? So let's evaluate this. So we got 0, 0, 0, and then the red one is 2 minus 2 times 10 to the 5. What are the units? Well, I'm still multiplying meters per second times nothing, right? Because this is a okay. So, all right. What I did here, I screwed up a little bit because I multiplied v. I took v cross r, not v cross r hat. Right, so this one literally said v cross r hat. I took v cross r. If I had done v cross r hat, I would have done 1 times 10 to the 7, 0, 0, cross product with 0, minus 1, 0, because it's going in the same, like the unit vector length 1 in the direction of the vector r. And you can figure that out, of course, it works just the same way as this one there. But if I worked out this one, that's fine, because v cross r hat over r squared, that's what's in the Biot-Savart, is actually equal to v cross r divided by r cubed, because r hat is r divided by the magnitude of r. That's how you get a vector in the same direction, but length 1. You just take a vector and divide by its magnitude. So, same thing, right? This is how we got a cross product. And what do we find? So what's important is the direction we get, like this was our final answer, the direction we get is the negative z direction. Right, so it's downwards. For the magnetic field, let's go back to the overall answer. The magnetic field at the front is 0. The magnetic field here is up. On that side, it's down. And you can check that with the right-hand rule as well. So different ways of evaluating it for here and here. In this case, they're both fairly straightforward. In some cases, one might be easier than the other. For example, if you can't immediately see what the angle is between the two vectors, because it's a kind of funny three-dimensional, direction, okay, just explicitly evaluate the cross product in components. Or maybe you're given the angle, you know the angle, then maybe this form is the easier one. Alright, so that was number 3. Make sure you actually fill in the details here as you did for your homework. So let's move on to the next one now. So here's number 8. In number 8 you've got a wire, and I drew it as if it were ending here, but of course the wire actually has to keep going, right? And there's a current flowing through the wire. I'm told the wire is made of niobium, and that is a metal that if it's super cool, at like 9 Kelvin or lower, it's a superconductor, like there's no resistance. To explain how that can be, given what we know about how wires work on the inside, you have to go beyond that model of bouncing electrons and really give it a quantum treatment, which of course is a bit beyond this course. But what we care about here is the fact that if the magnetic field at the surface of this wire becomes bigger than 0.1 Tesla, then the superconductivity breaks down. So you want to know, like, how much current can we run through it so that the field on the surface has 0.1 Tesla or less, right? But because we care about this limiting case, we're going to say the magnetic field at the surface is exactly 0.1 Tesla, like the upper limit. What therefore is the upper limit of the current? So this one is actually fairly straightforward once you understand what's going on. The magnetic field of a wire is given by this expression. This is something you can derive either from integrating the Biot-Savart law along a wire, like adding up lots of tiny little charges as you go along the wire, similar to the kind of calculation we did for calculating electric fields from an infinitely long wire. before we knew about Gauss's law. Or, just like there's Gauss's law for electrostatics, you can use Ampere's law to get this in a, almost like, just like in your head, this calculation, to derive this. But there'll be a separate video for that. So, if the current is this way, you can use the right-hand curly rule to figure out, if it goes this way, then it's curling around like above here, right? My finger come up above the wire. If you mention my thumb was actually right inside the wire, my fingers would curl underneath it. So the field is something like this. Right, that's kind of the magnetic field. If you try to visualize it in 3D, of course, it's also like further out. So it gets kind of hard to draw in 3D, but you get the idea, right? That's the magnetic field. Now, that is true. This expression is true as long as you're outside the wire, right? If little r, the distance from the center is smaller than the radius of the wire, so you're inside the wire, still fairly easy to calculate. But you have to use Ampere's law here to actually work it out. This expression applies as long as you're outside the wire. So if you write on the surface, though, you're still outside the wire. All the current is still inside the loop, right? So this loop, right on the surface, I will draw it like this. There's still all the. It's just on the surface the magnetic field right there, right? So in that case, if you're on the surface, we have the distance from the center is the distance from the central axis, right? Is just the radius of the wire. So you just plug it in from there, and that's all you need, right? It's really the insight that the magnetic field right on the surface is still the same expression as this. Can you imagine I get closer and closer to the surface, right? And this expression holds. If I'm 0.1 millimeter, 0.01 millimeters, 0.0001 nanometers, it's still fine. This expression holds. So right on the surface, little r is big R, the way I've denoted it. You know the field strength, so you can solve for the current. Super straightforward once you visualize what's going on. The whole thing about superconductors, interesting stuff, but in a way not needed for the problem part of this. Alright, you should be able to take it from there. Up next is number 12, which has the following setup. You've got two wires, and the way this is drawn is that the wires, they come right out of the page, they go into the page, right? So remember those symbols, this little dot means the currents coming straight towards us, like this. The cross means the current's going into the page like this. So it's pointing down here, up here. So maybe this is circuited, so it goes up, across, and then back down. And then goes, under the desk or something like that. Doesn't matter for our purposes. Wire comes up, current goes upwards here, downwards here. That's what those symbols mean. We are asked to find the magnetic field at each of those points. I think this is called point A. Which one's A? Let me double check. Yes, A, B, and C. Right, and the distances are 1, 2, and everything here is in centimeters, so make sure when you do your calculation later, all distances are in centimeters. So care, distances given in centimeters, so you need to convert. So how are we going to do this? If it were just a single wire, right, it would be super easy. This one, let's just take this one. By our right-hand curly rule, the current is up, so my fingers point this way around it, but my thumb points in the direction of the current. My fingers point this way, so the current, essentially, we just draw like maybe, not the current, excuse me, the magnetic field, essentially does something like this. It goes around like this. And we know how strong it is, right? Because it's a wire, a straight wire, so the field is given by the same expression that we had in the last question. We write it down, and we're going to need B wire. I guess just the strength of it is mu naught I divided by 2 pi r. So let's look at each point. this one here is going to create a magnetic field that goes around like this. So just by looking at the geometry, it's going to create a magnetic field here in that direction, just a bigger circle like that. Here it's going to create a magnetic field in this direction, right? Because if you imagine there's a circle, big circle that goes right through here. And this one is going to be stronger than this one, right? Because the R in each case is this line here, which is longer than this line here. Of course, you figure out from the geometry what that length is. And over here, this one's going to point in this direction here. And because of the setup, like distance 1, 1, right, you can immediately see those angles are all 45 degrees and 90. So it's super easy to actually work out what the distances are. Now the other wire here is going to add to that though, right? This one goes down, so the current goes down, so my hand curls the other way. It curls like clockwise as you see it on the page. So this one is going to create a field that looks essentially like this, right? All around it, further out as well, getting weaker as you get further away from this one. So this one's going to create a field over here that essentially does this. Over here, it's going to create a field that does this. So they're in the same direction, the red one, because this one going counterclockwise, right, adds to this one going clockwise because it's right between them from the geometry, right? It works out that way. And this one here is going to have a field that essentially points like this. Now for each one, you can find the strength using this one. This expression here, so you're going to do it like 6 times, although it should be fairly easy because many of the values are the same. And then you add them, but you add them as vectors. So make sure when you add those, for example, you can immediately see by the symmetry of it all that the vertical component is going to cancel out, but the horizontal component is going to add. Same thing over here, whereas here they're just going to straight up add because they're in the same direction. So you can fill out the details here to complete that question. Let's move on. Questions 20 and 21 are about evaluating line integrals, right? That is a concept you're going to be studying in full in one of the more advanced calculus courses, like multivariable calculus somewhere. But we're going to just get the basic idea here. So what's asking us to find is the line integral of b between the point I and f, initial final, right? So line integral of b between I and f, right? That is literally what it's telling us. So what is that thing? What it means is, right, I'm going to take the dot product of b with each step. So I'm imagining I'm walking along this line, and the line I'm walking along here is straight. Makes our life a bit easier. And I'm going to take little steps. Each step I'm going to call ds. Let me use a color for that, maybe green. Right, so little steps. The steps I'm taking, of course not little bows, little tiny, straight little steps. Each one little step is a little vector ds. Right, I call it little d because I imagine it to be infinitesimally small. And I'm going to add them up. So I'm going to evaluate the dot product of this. I'm going to evaluate it a zillion times as I take tiny steps from here to here. For each step, I work this out where this is my step displacement from here to here to here to here. Each one is little ds. Each time I multiply it by I take the dot product of it with b. And then I add those up, but because of infinity of them, I'm going to have to integrate, and it's going to be from I to f. So that's what I'm asked to do here. Now, let's look at the magnetic field for a second. Now, the way it's shown, right, it's showing us these blue arrows, they represent the magnetic field. What about over here and over here? We're just not given information, right? So over here, the magnetic field, maybe it looks like this too, or maybe it stops being uniform. But we don't care because our path is not taking us around here, right? If we take a different path, you might have gotten a different, you would get a different answer, possibly, right? So the path matters. It's not just the initial and the final point. In general, the path that you take matters when you evaluate a line integral, or it's also called a path integral. Let's actually evaluate this. So the nice thing here, right, is that b and these little steps, they're in the same direction. So here, b is parallel to my step direction, my little ds, my step. That's my step displacement. I told you early on in this course, this is where you learn to actually understand what integrals mean, right? So here you go, line integrals. b is parallel to ds in this case because of the setup. So what does that mean? b dot ds, for any one of them, doesn't matter which ds, the first step, the middle step, the step over here, the last one, doesn't matter, because they're all in the same direction, and the magnetic field is always in the same direction. So whether I'm here or here or here or here, both of them are both the same every time. So I only really have to evaluate this once, and I'm doing it right now. So I'm going to get the magnitude of b times the magnitude, let me write it out specifically like this. The magnitudes multiply times the cosine of the angle between them. So theta is between b and ds. We write it like this. That's just going to be the length of this and length of this. The angle, what's the angle? The angle is 0. Right, so the cosine is just 1. So I get b, the magnitude, times just ds, the magnitude. So now my life is easy, because then my integral becomes, I'm not sure I call this integral, I'm going to call it I for integral, but let's call it my line integral, Li. I want to get that Li, that my line integral, is equal to I dot f times b, the magnitude of it, the step size, but because b is constant, it doesn't ever change, I can take it out front. Then I've got the path from I final to, from the initial to final, just ds, the step size. I'm writing it like this time. So, but this whole thing here, right, is just the path length. Because if I add up the individual step sizes each time, no matter how tiny my steps are, I start here and here, my total steps have to add up to exactly this distance. And in the actual question, you're given values. Right? You're given essentially a position here. In my case, it's 50 centimeters. And up here, it's also 50 centimeters. So make sure you figure out how long this path is. Notice the path is not 50 centimeters long, right? It's the diagonal. You figure that one out. The path length here. Right. So you can just plug in the value here, 0.1 Tesla, work out the path length, that's going to be your answer. That works because it's so simple, because the magnetic field is always the same direction, path, steps. Each step is always in the same direction. So I only work this out once, and the angle is super easy. The angle, this cosine gives me 1. You take b out of the integral, and all I've got left is the path length itself. And that's just geometry then. Alright, now number 21 is kind of similar, except that now the magnetic field points the other way. The magnetic field now is perpendicular to my path. So what does that mean? Well, I want to evaluate the same thing, right? So let's do this. I want to evaluate I, initial to final, initial position to final position, b dot ds. And my ds, right, are my little steps as I go from here, here, to here, to here, those tiny little steps. Each little ds is a little vector from here to here, infinitesimally small mathematically speaking. Of course, I can't draw it that way, right? I have to draw the small vectors. And again, just like before, the situation is the same here as here as here, right? Always the steps are in the same direction, and the magnetic field's in the same direction. It's just not, the two of them are not in the same direction. But as you go from one step to the next, neither one changes their personal direction, as it were, right? So what is this, right? So we're trying to figure out B dot ds for any one of them. Well, it's going to be the magnitude of B times the step length times the cosine of the angle between them, between the magnetic field and the step. Well, this is 90 degrees, right? That means this is 0. Well, now I don't care what those are, because the whole thing is just 0. So each individual one is 0, so what I'm going to get this thing here is going to be from I to F, B, the magnitude of B, times the step size, times 0. Well, that's a bit boring, isn't it? It's just 0. So this line integral here ends up just being 0. There's not much more to evaluate, because the path is always perpendicular to the magnetic field. So each individual little step adds that much to the total sum, the total integral, but you just get a bunch of zeros. They all just add up to 0. So those are 20 and 21. This concludes the part 1 of the homework preview. In part 2, I'm going to start with question 22. So I will see you there.